Hey all, Happy New Year. Welcome to 2021. I thought that for the first video of the new year, I would do something a little bit different from what I would normally do. And I'm going to kind of peek under the hood of what's going on in Elixir and Erlang when you work with files. This is a really fascinating subject because Elixir and Erlang do things very differently from most other programming languages. The way it's done is primarily in the service of making sure that when you do concurrent access to files, things don't go off the rails. And let's go ahead and do it. So first thing I'm going to do is I'm going to show you that in this directory I've created a file called foo. And it's basically just got one line of text, a bar. And let's go ahead and open it using Elixir. So I'm going to start up a Elixir terminal, and then we're going to just do it this way: file.read foo. Okay, so here we can see that if we call file.read, it will open up the file and give us the contents of it. Pretty straightforward. Now, you might not necessarily want to, this is the easiest way to access file contents in Elixir, but it may not necessarily be how you want to do it. Like, for example, let's say you've got information coming in on an asynchronous channel, and it's coming in, and each time the data comes in, you want to append information onto the file. And in that case, you would want to open the file, perform multiple operations on it, and then let go of the file at the end. In most programming languages, the way that you do this is with some sort of file open. Then you do your individual atomic operations, and then you close the file at the end. And closing the file is really important because the way that your operating system manages files is by giving each process something called a descriptor, which is usually a number, and it represents that resource in the programming in the operating system. And the reason why this is important is because the operating system wants to keep track of a limited number of files at any given time. It needs to do that because if two programs are writing to the same file, you're going to have a problem, or you could potentially have a problem. And so being able to manage that sort of contentious resource is what a file descriptor is for. So the equivalent operation on that in Elixir is file.open. And so let's open the file foo. The first interesting thing that you should notice is that you don't get back what you would normally consider to be a file descriptor. It's a PID. And we're going to poke at that a little bit later. You can get a file descriptor out if you open it in raw mode, but I'm not going to explore that in this video. Now let's go over to the other side and see what the operating system thinks about what we've just done. So what I'm going to do is I'm going to use a program called LSOF, which is list open files, and that gives you a list of all of the open file descriptors that a program has taken out in the operating system. So first in order to do that, I need to grab the operating system process ID. So to do that, I do ps-aux, and I'm going to grep for beam.smp. And here's the beam program that I'm running. And now I'm going to LSOF. And look at that. So we can see that LSOF is aware, or at least the operating system is aware, that I've opened up this foo file in my on this other side. Okay, so that's how that works. Now let's do something a little bit different, and this will begin to demonstrate how Elixir and Erlang is different from other programming languages. So what I'm going to do is I'm going to spawn a process, right? And after I spawn the process, so in the process, I'm going to open the file, and then the process will exit naturally. So that gives me the PID of the spawn process. And let's do the same thing as we did before. So first I'm going to grab the PID, the process ID of the of Elixir, and then I'm going to LSOF it. And what you'll notice is that that file, the foo file, is not in my list of open file descriptors. So that's really interesting. I never called any sort of cleanup where I closed it, where I closed the file, and yet it's no longer holding on to it. Well, let's just first double check to make sure that what I'm doing is correct and that I actually have opened it in the first place. And the way I'm going to do this, I'm going to change the spawn function just a little bit, right? So we're going to confirm that this is open. And so once this process is spawned, the first thing it's going to do is open the file, and then I want it to block. And the way to create a block in a process is with the receive command, instruction. So I'm going to receive, and what I'm going to do is I'm going to have it be passed just some token. So we'll call it wait, and then this output is not important. And so what this spawn process will do is it'll open the file, and then it'll wait for me to send it the wait atom. And then when it's done, it'll fall through at the end of the function. And presumably, the effect that we'll see is that while this process is held open, I should be able to see that the file descriptor is open on the right hand side here. And then when I send this process the wait atom, it'll get cleared. So let's do that. And I'm going to LSOF, and you can see that the file is open. And then what I'm going to do is I'm going to send the spawn process the atom wait. By the way, if you aren't aware, V is like the ANS key on your calculator. It just gives you the result of the previous instruction. And then now if I do this, the file foo is clear. Okay, so that's how that works. So one other thing that I want to do is I want to show you how this how it makes sense that this thing that represents the file is a PID. So let's poke at that a little bit. In order to do that, first thing I'm going to do is I want to show you a different way of using the PID. So we can, in fact, use the PID as if it were a file descriptor in other programming languages. So first thing I'm going to do is I'm going to open the file again. But this time I'm going to open it in write mode. Right? And now I'm going to pass this as the first parameter to io.puts. So you might normally use io.puts to send something to the console, but it does have an optional first parameter, which can be an IO object. In this case, we're going to give it this file descriptor PID, and that'll send information to that file in the io.puts. So io.puts the previous value, and then we're going to put in, what do we have in there before? We had the word bar in there. Let's put baz in. Okay, so on this side, I'm going to cat foo, and now you can see that indeed the word baz has been written to the file. So this is pretty basic. This is how io.puts works. Now, the next thing that I want to do is I want to understand exactly what the heck is going on when I send a PID to this io.puts. So how can we do that? Well, what I'm going to do is I'm going to write a process that just traps whatever message gets sent to it. Pretty easy, right? Spawn, and then receive, and then we're going to io.inspect it. Okay, so now just real quick, let's take a quick look at how this function works. So if I can send the foo, it's going to io.inspect foo, and this here is the result of the send. So let's go ahead and rerun that. And this time I'm going to io.puts. So that's pretty cool. We got this thing, IO request atom. It's a tuple with the IO request atom, some PID. I'm guessing that's myself, a reference, and then a payload of put cards, Unicode, and then whatever I did the IO.puts. Let's just verify for a second that this PID is actually self. And yep. So basically this here is a callback. It's like a return address, right? So this pattern, PID and a reference, is typically, hey, when you're done, send it back here, and then this reference is how I know what you're referring to. So this is the return address and the line for the subject line for an email or a snail mail. That's the equivalent. So okay, the last interesting thing is that we got this weird terminated thing, and maybe to understand that, I guess the first thing to look at is that the thing that terminated was io.putcars, which is wrapped by io.puts. And maybe the way to think of that is that let's make a hypothesis that I was supposed to send something back. So io.putcars sent a message to this PID, and then it took out a monitor against that process. And if nothing came back, it kind of freaked out and was upset. It was expecting a response, but instead this process that it thought was a file descriptor just kind of died. All right, let's test that hypothesis. And the way I'm going to test that is I'm going to add an extra receive in here. So that's going to do and then let's do the same thing. So we're just going to io.puts to it, and then so we got that result of the io.inspect, which is printing this to the screen, and then it's held open because I need to send it await, and I can't do anything. So basically my terminal process is locked up, and so that's kind of, I think that's a good model for what's happening. So basically what's happening is that I have the io.puts is sending this message and then expecting a response, and it's not getting it. So let's take a peek at what sort of response we might expect it to have. And so how are we going to do that? What we're going to do is we're going to open up another file descriptor, and then let's do foo again, and then we're going to open it for writing. And this time, we're going to manually perform a send, pretending that we are io.puts. And so how do I do that? Basically, what I'm going to do is I'm going to reconstitute this, this message. So here's how I'm going to do it. I'm going to make a tuple of io request with myself as the second element in the tuple, and then create a new reference, and then the put cars tuple at the end. All right, so that gives me that value. Now I'm going to send that value to the result of file.open, so that's v1, right? v1. And then let's send it v2, which is this thing. Great, so that succeeded. And then so now what we would expect is for the file to contain the word foo. And that's correct. So I basically mocked out what's happening from what would normally have been an io.puts. So what we would expect is to see a message inside our message queue, our console message queue, which is equivalent to what we were not able to send when we had our own little fake file descriptor. process. Let's find out what that is. And here we go. So we see that there's an io reply message sitting in there with a reference that is exactly the same as the reference that we sent it. So under the hood, when you open a file and perform file operations with it, there's a lot of really cool coordination things that are happening. First thing happens is that it creates a PID. There's a PID that gets created, which is there to monitor that handle all communication with your files. And the nice thing is that you can share this PID with multiple different other processes. So different processes can concurrently write into this file. Of course, only one of them is sort of the process that's in charge. This PID that is handling is sort of the nexus for communication to that file. It monitors the process that created it, and so when that process goes down, it automatically performs a set of file close. You can also manually close those files if you want, but you don't have to. You can be lazy. And the other nice thing is that it's unlikely for you to have an accidental file descriptor leak, a resource leak, because the Beam will take care of these things for you. Then, in order to perform an actual operation against that the file monitoring process, what you will do is you will send this IO request message, which contains a return address and a reference to itself, and then whatever instruction for what it should do as a structured data type. And then the IO operation itself takes out a monitor against the file program, so that if something weird happens, like the file process dies or some sort of error gets thrown, it itself gets communicated that message as well. And then it expects to see this IO reply, and the IO reply contains that reference to the request. And the reason why you do that is because if you happen to have some sort of weird stray messages hitting your message queue because maybe some operation failed or you thought it failed, this could happen across a network. So maybe you're sending a write request to something that lives across the network on the other side. You receive some sort of message that the node is uncontactable, and then you think that your process thinks that it's gone, and then the network comes back, and then your your reply comes back to you, right? Then you do another file operation. You're going to be in trouble if you don't also selectively if you aren't selecting against the correct reference, because how do you know that the reply is coming from this weird network disrupted connection pattern versus the one that you just sent most recently? So the designers of Erlang and Beam have thought about all of these problems. This has been solved for decades even. And yes, this does incur overhead over writing straight to a file descriptor, right? So, you've got to package up this weird message and send it across potentially networks and stuff like that. But if that safety is worth it to you, then you should be using the standard file open. If you need performance, then you can use the raw method, which really does handle things over with file descriptors. And of course, they're local, so you can't do transactions with raw files over Erlang clusters. There are other programming languages that are designed for distributed systems that really don't have a lot of these features. They don't give you this level of safety and this level of coordination across a cluster. They don't take into account the reality that network problems happen, and you can't rely on network connectivity. And the other nice thing is that because each of these is sent as a message, you know that whenever you do an io.puts command, that content is atomic. So the Beam treats writing to the console in exactly the same way it does to writing a file. And so if you are in a situation where you like have a paragraph's worth of information in some sort of log to tell you that an error has happened, or maybe you're keeping track of some data type that is several lines long, you don't want to be in a situation where concurrent processes that are trying to send information to the console interrupt each other, right? And I remember that this was a problem in early versions of Go, and it drove me up the wall trying to debug things, because if I tried to print things to the screen, I would start printing something and then it would get interrupted by another Go routine that would inject its own text in between, and I could never make heads or tails of what was going on. And it's not a problem in Erlang and Elixir, because each of these writes is atomic in and of itself. So I can send a paragraph of information to console and it will be undisrupted, even if another process is trying to send information to the same console. Okay, so I hope you found this video to be entertaining and interesting and knowledgeful. If you like these sorts of videos, let me know. Hopefully I'll be making more of these over the course of the year. Thanks, y'all.